All right, in part one, yesterday we looked at examining gravitational potential energy in a slightly different light. We've done previously in our energy discussions, we've talked about potential gravitational energy right next to the surface of the Earth, and then yesterday we expanded that discussion to what if you get a long way away from the center or the surface of the Earth? So we start talking about radiuses of Earth away, and that's what we have up here in this little graph. So this discussion is a little bit more about when you get into more space-related and farther away from the actual Earth or Sun or whatever the object you're dealing with is. So this is a graph that we looked at yesterday or in the previous video describing the gravitational energy. Some of the highlights are that these are all negative values. So your gravitational potential energy as you sit there in your classroom is a negative value. So let's just say you're sitting in your classroom, you could say it's negative 100 joules, which is totally not the right answer, but just so we have a number to play with. As you move further away from the Earth, so this is one Earth radius, or you're at an Earth radius, two Earth radiuses, etc. You'll notice there's a blued out marker here. You can't go deeper into the Earth. The mathematics doesn't hold. The conditions don't hold. You'll have mass all around you. There's a whole bunch of things that deviate or change. So this expression over here doesn't work when you start to dive or drill into the Earth. So this is the surface of the Earth here, and this is as we move one radius, two, three, four radiuses away. So when we look at stuff like this, as you get higher and higher, we're pretty comfortable, I think, in that if you lifted your pencil off your page or off the desk and you held it up in the air, you've done some work. You've increased the gravitational potential energy, and when you release that pencil, that gravitational energy is changed into kinetic energy, and it transfers back in. So as you raise that pencil up, you might move to, say, negative 50 joules. And again, I'm just making up numbers for the sake of discussion. When you look at this, though, this is a change in energy of positive 50 joules. And that's the interesting piece, is that we are increasing our gravitational energy. It's increased here. It's the change is a positive increase, but the actual values themselves are negative. And that's a really tricky thought that we encountered in the first part of this video. So let's just go back in here and take a look. So the negative right there, the negative values of this potential energy is characteristic of something called a potential well. And you may have heard that term in science fiction and other articles, maybe the idea of a gravity well. So it's an idea that when you get into the potential energy curve here, and we'll see this on the next slides or two, you need a certain amount of kinetic energy to either stay in place or to escape it. And that's what we're going to look at today, is how do we interact with this potential well, and how do things in space stay in space, how do they travel in space. So when we say a potential well, you may have seen objects like this. There's a little video link here, it's on the calendar as well. And it's the idea that objects with mass warp or bend space-time. And that's a whole other discussion that'll be, you could have a course alone on that particular object, but just so we have a little bit of an idea, here is the idea of that this shape right here, this curve, this red curve, spun or rotated in 360 degrees. So a satellite, for example, might be here. Let's change back to a marker. And its orbit might go around on that line right there. Okay, so it would be at that location, and that was where its orbit would be. Another little demonstration, the more mass of the object, the bigger the change in that potential well. You can imagine it as deeper, but you can also think of it as steeper as well. Another representation over here. If you check out the video link, it's just a neat little, it's kind of an ad actually for a product that helps to illustrate what a potential well can look like. So let's start with talking about escaping Earth's potential well. And this extends to other celestial objects, but we'll just use Earth because it's easier to talk about. So to escape Earth's potential well, the kinetic energy must be more than the Eg. So our gravitational energy, highlighted on the graph. So if you look here, in green I have Eg. So this is a certain amount of gravitational energy. If I want to escape, and that means get out of the gravitational pull, get out of the potential well, and not be affected by the potential well, then I need to get to what we call zero. Which, again, when we're talking about gravitational energy, zero is actually a big number. It's kind of weird because if you're down here at negative 100 and you're up here at zero, zero is technically bigger. It's higher on the number line. It's higher, so it's a larger in magnitude. So let's just get rid of those dudes. No, I shouldn't say larger in magnitude. It's just larger in terms of the number line. So that's a tricky thought. So if we want to escape from Earth, we need to have enough kinetic energy that we can get to this zero line. And so if we set our total energy and we fix that as being constant, or set to zero, pardon me, right here, then our EK plus our EG must equal zero. So EK equals the negative EG. You can set that up with our standard kinetic energy formula and our new gravitational energy formula. And the double negative here is important to see because it cancels out, especially when we go to do the square root sign. That's important. And you can actually come up with a value. And this is, I think that should show up on your page. Here, I'll raise it up a little bit. About 11.2 kilometers per second. Now, again, this depends on how high you're trying to get to, things in the air, and this isn't like a precise number. It's an approximate number, but it'll give you a good idea of what it takes to, this is literally throw something or catapult something or hit a golf ball or spin something and chuck it into the air. Not a rocket. That's not what we're talking about here. This is about pick up a baseball, and if you can throw it at this speed and you have enough energy in it, then you could potentially throw it into space. But remember, 11.2 kilometers per second is incredibly fast. So that's what we call escape speed. So escape speed, I could probably make this a tiny bit bigger. Escape speed is the minimum speed needed to project a mass m from the surface of mass capital M to just escape the gravitational force of m. So it's a theoretical idea that if you could throw something that fast or project something that fast, you could throw it or get it out of the potential well and get it into either orbit or further away and just get it into space. So escape energy is the minimum kinetic energy needed to project a mass m up to that location. So one is a speed, one is an energy. If you look back here, you'll notice that the speed is not dependent on the mass of the object. So the speed, oops, I gotta bring that back up here. You can't see that. Let me go. Here. This speed down here, if you look at the proof, is independent of mass. The mass of the object canceled out. So this speed, golf ball, tank, hippopotamus, whatever, if you can get it moving at this speed, you could in theory throw it into space. Having said that though, the more massive an object, the more energy it requires. So there's a big difference between those two ideas. And then we have something called binding energy. So the amount of additional kinetic energy needed by a mass m to just escape from a mass capital M. That's kind of an orbit related. So if you imagine a satellite in orbit, if you gave it just the right amount of binding energy, you could get that satellite to break free of its orbit and travel into outer space further. So please note, we're not talking about a rocket. So rockets flying away are different than satellites. Rockets are not things that are thrown or projected into space. They're very different. Having a rocket go into space is a much more complex system. There's changing mass, there's changing forces, there's drag. It's just so much more complicated. So we're just talking about either projecting, throwing something into space, like spin launch does. If you haven't had a chance to check this out, it's kind of cool. So there's a video link here. I'll put the video link on the calendar as well. But this object uses a centrifuge, spins objects ridiculously fast, and then launches them out the tube at the top. Now, it obviously can't throw large objects. It can throw like missile sort of size things, a couple feet long, so small payloads, but no rockets required. So you can spin things really fast and boom, shoot them out the top. So if you check out the video link, it's kind of cool. It's even worth going to their website and seeing some more of the the things that are going on. It's really remarkable. So something to check out, spin launch. Okay. So let's go to bound objects, which is satellites. So we've talked a little bit about throwing an object in space. We've talked about the speed sort of required to do that, but bound objects is where we find there's a lot more human use. So we're normally talking about satellites. There are literally hundreds, if not thousands, of satellites that orbit our planet. Our planet orbits the sun, so there's a lot of information there that's important to understand. Make sure I can fit everything on here. So if we start with a quick little proof, when we have a satellite orbiting, okay, and we talked about this in class already, if you have a satellite orbiting a planet, a sun, whatever it might be, there's no extra energy being put into that. They don't have a giant fuel tank that they have to keep filling up. Satellites are in space. Yes, they have solar panels that generally keeps their their electronics running, but once the satellite's in orbit, it doesn't need a lot more energy to stay there. Okay, and the only force that's keeping it there and has it falls through space, and again we talked a little bit about that, is the force of gravity. So your F net, your summation of your circular orbit, is set to the gravitational force. So you can see we can set these two things together. And more things would cancel, but we're not going to. So what we want to do is we're just going to stop here for this proof, and we're going to relate that the mass, or mv squared, equals gmem over r. Okay, and just we're going to pause on that thought because we're going to link it down here as something else. So the total energy, and remember this is the concept of total energy we introduced back here. If it's 0, we can escape. So if the total energy of the satellite is constant and not 0, we're going to have it as some other value other than 0 because we want to stay in orbit, we don't want to escape, then we can set Ek plus Eg. That's just right here. If you write in the traditional formulas, Ek is 1/2 mv squared. Our new gravitation is gmm over r. We can make a substitution for this guy right here. And we're going to pull that from above. And so what you see is we can actually replace the mv squared with the gravitational relationship. And what do you know? We actually have like terms. So here we are now with like terms in a problem, and they can actually be reduced. So you have 1/2 minus 1, and you end up with this expression that says the total energy to stay in orbit, the total energy right here to stay in orbit, is 1/2 of the gravitational energy at whatever height you've chosen. Okay, so ET can be negative. That means your total on your graph right here. Here's your EG graph. Your total can come in somewhere down here on the negative side. Doesn't have to be 0. Okay, so ET for an orbiting object is equal to half the gravitational potential energy at that given distance r from the main object. Okay, so here's what it kind of looks like. So if we were to look at, let me grab my highlighter here. Here's my total energy. Okay, so we have Eg, which is the gravitational energy at, in this case it looks like we are somewhere between 1 and 2 Earth radiuses in orbit. So we're somewhere out in space and we're orbiting Earth. Well, that has a certain amount of energy, and gravitational energy. So the required total energy to stay in that orbit is 1/2 of this Eg. And so, well, how do we get to that? Well, we need an Ek right here that when we add the Ek to our negative Eg gets us to land at this line. Like that's some pretty difficult thinking. We're used to all of our energies always being positive for most of our questions. Now we're starting to find out that, wow, our gravitational energy is always negative. Our Ek is positive, and then our total energy can be negative. So let me just see if I can bring that up a little higher for you. There. So in summary, the total energy of any object in Earth's gravitational field is composed of kinetic energy and gravitational energy. So those two pieces. It's moving and it's bound in the potential well. And then to be stuck in an orbit means you're using about half, your total energy is half the gravitational energy. But there's a couple of different outcomes that can show up from that. Here's the possible outcomes. I'll bring the third one up in a minute. If ET is 0, so what that means is if your kinetic energy right here, and I'll pick it up and move it, if that kinetic energy exactly matches your gravitational energy, then you end up on the 0 line. And if you end up on the 0 line, then you've escaped. You're just outside of the potential well, and you're not being drawn in, but you're not going anywhere else. So I'm using these to scale. So this is a positive value up here, this is a negative value, and anywhere you look on this graph as you move along, the vertical and the right here, so if you took this guy and the one down here, these would be the same height, same values, opposite sides. So the second case, you have a total energy that's greater than 0. So now you're looking at a case where your kinetic energy, I'll draw a line and I'll drag it. You can see your kinetic energy is bigger than your gravitational energy. And so you actually have more kinetic energy. So not only do you escape, but you can actually depart or leave the Earth in this case. So you have more than enough energy to escape the well and fly off somewhere else. Now the third case, and this is the one we're presently talking about, when we talk about bound objects, is what if your total energy is less than 0? So this is an object bound to Earth, and you can see, I'll draw some lines on here. If I take my kinetic energy right here and I drag it down right there, that positive amount of kinetic energy, and I could probably even throw a number on that if that helps this illustrate it. Let's say this is plus 100, making this up. This is negative 120. So when you bring down that plus 100, you end up getting a negative 20 here. And I guess we could, yeah, we'll just do that for illustration purposes. I'm not checking that over very closely, but just so we can see how the numbers sort of behave. So don't hold me to that just yet. So I'm going to get rid of those just in case somebody wants to try and tie me to that. But this is the case, is that the total energy is less than 0, and that's a satellite. That's a bound object. All right, so let's try. This is an example from your text. I'm not going to read the whole thing. I've already got 17 minutes, so pause it, read it, or grab your textbook and go through it. It goes through all the different cases that we're going to try and look at. So what is the radius of a satellite, gravitational potential energy, the changes, the total work done, all those key questions that come with this type of problem. So pause it, take a look, or just pause it, go pick up your textbook and have a quick look. And it goes all the way down. I have to throw the bottom part up here. And the second part of the question is here. So you can pause it and read the first part, and then I'll slide up the last question. Okay, so we can pause that. You should be able to see most of those questions. All right, so we can't really talk about a gravitational well without talking about this one, a black hole. So a black hole is a very dense body in space. It has a gravitational field so strong that nothing can escape it. At least that's our current model. That's probably going to change, or it's already probably in the process of being changed. As we currently envision them, though, once you get dropped inside the gravitational well of a black hole, even light doesn't escape. Now, I'm sure we're going to find something in the future that does get out of it if they haven't already. That's just nature just doesn't seem to have a terminus. Nature always seems to be cyclical. We just may not be able to see it yet or figure out where it's going. So a couple key terms that are kind of fun in video games and movies. The event horizon. So that's the edge. That's the edge of the well. Once you slip past the event horizon, you're going for a ride. Singularity, that's the center. Get my joke? You can't see me. And then the Schwarzschild radius, that's the distance from the center of the singularity to the event horizon. Interestingly, though, and this is kind of a patriotic moment, but the first black hole discovery was in 1972 from Professor Tom Bolton while working at the University of Toronto. So kind of a neat thing. I was looking into some other stuff with source of X-rays, and it turned out to be one of those huge discoveries. And it started a whole interesting section of astrophysics devoted to what happens at black holes, where do they go, how do they it's a very large topic, super interesting too, but not totally within our course spectrum at this point in time. So summary, what things you want to try and take away from this section. Again, right from the textbook. Feel free to flip to it and have a read, or pause it here and read these ones. And then a couple questions to try. Hope that piqued your interest. Check out some of the videos that are linked, and by all means search for some more. Thanks.